In activity 8, we are going to look at the transfer characteristics of a NOT gate. In other words, we're going to look at what point a high becomes a low and a low becomes a high. We know that with a NOT gate, when the input is low, the output is high. When the input is high, the output is low. But at what point does that switch over? When does the NOT gate recognize that it is changing from a low to a high going in? Well, this little circuit will enable us to do this. Once again, we're using a potentiometer because we are using it to vary the voltage into the NOT gate between its maximum 5 volts and its minimum 0. So we can adjust this voltage all the way between those values. So we're going to use a voltmeter on V in and we're going to use a voltmeter on V out. So what I have here, I have my 2 voltmeters set up. This is V in and this is V out. At the moment V in is 0 and therefore we know that V out should be 5 volts, but it's clearly 4.96. So when I change V in, and I'm going to change it all the way, so now I have V in at 4.96 volts, my output has gone low. So a high in, a low out, a low in, a high out. So I'm going to write down that value to start. Now it doesn't matter if we can't get to exactly these values in the table, as long as we write them down as they are on our voltmeters. So at the moment I have 0 going in and V out is 4.96 volts. So now I'm going to go to 0.5 volts V in. So up I go. That's pretty close, 0.51, and my output is 4.96. 0.51 and 4.96, and you'll see that V out hasn't changed. Next I'm going to go to 1 volt, 1.03, 4.96, 1.03, 4.96, 1.5, and I'm going to actually just keep going here because you notice that V out is barely changing. I'm going to go up to, let's go up to 2 volts. So 1.97, 4.82. 1.97, 4.82. So V out has dropped very slightly. Let's go up to 2.5. 3.43. 2.5, 3.43. 3 volts. So 3.04, and you can see that V out now has dropped all the way down to 0.12. So at 3.04, that has dropped to 0.12. If I now keep increasing V in, you will see that V out barely changes. I mean, 0.12 was quite a small value. 3.5 gives us 0. And we know that none of those values are going to change V out now because, of course, it can't get any lower. But if we look here, between about 4.82 and between about 1.97 and between about 3.04, we obviously had a quite varied change because this changed from 4.82 to 0.12. So let's take a few readings in between 1.97 and 3.04. Let's go back a little bit. There we go. So it doesn't matter what readings I take. Here we go. I'm going to go to, let's say, 2.34 is 4.41. 2.34 is 4.51. Go a little bit, change a little bit more. 2.5 we've already done. I'm going to go, let's go to say 2.85. 2.85 is 0.22. Let's go up a little bit more. All this will allow us to do is to take a reading somewhere and see. Oh, no, wrong one. Oh. There we go. 2.64 is 0.441. 2.64 is 0.441. So what I can do, I can plot those results now into my graph and have a look at the transfer characteristics. So if we have a look at our results here, here is my graph that I've drawn based on what we've just looked at. And we can clearly see here that as we increase the value of V in, V out has gone from a high at 5 volts down to a low at 0. At what point of V in did it change? Well, it starts to change somewhere around here, and it's pretty much changed somewhere around here, which is in between these dotted lines. And they are in between about 2.2 volts and 2.7 volts. So we can see from our NOT gate that anything below 2.2 is considered a high on V out, and anything above 2.7 volts is considered a low on V out. Arguably, you might want to look at it from the point of view as V in, that anything below 2.2 is considered a low, and anything above 2.7 is considered a high for V in. However, irrespective of our results, the data sheets to do with the 4000 series ICs generally give anything on an input above 70% of the supply voltage, so above 70% of 5 volts in our case, as a high. Anything below 30% is considered a low, and therefore that gap of 40% is considered almost no man's land. In other words, the CMOS IC won't recognize that supply voltage. And our output should have been at supply voltage, which it pretty much was, and the logic 0 output should have been at 0, which it pretty much was. There's other characteristics here to do with CMOS chips, and it's well worth having a little read and understanding them, because they inform your decision as to which chip you might choose in the future. One of the reasons that we looked at this particular experiment is because quite often we mix analog signals with digital signals. And therefore you may at some point be putting an analog signal that might be, say, 1.5 volts or 3.5 volts in, and would you be able to mix this analog signal with a digital signal, and the digital component able to recognize this analog signal as a signal that it can deal with. This is the end of the digital electronics tutorials.